Alright everyone, let's break this down step by step. First, let's cover some key functions to make sure everything's clear. Once we go through this, it is important that these fundamental basics stick with you since we use them constantly in industrial robotics. These definitions apply to any industrial robot you will work with, so get comfortable with them, okay? Today we will focus on motion curves. Now remember, the max speed shown here, which Vmax, it is directly the speed you use in the program. So let's use a placeholder value for now to focus on how Vmax speed works. Here's the individual axis speed, and here's time. Okay, so the max speed displayed here matches the speed you program that point in the program. Okay, so let's zoom in this. They're lined this lead axis here. What this red axis here says, it's the axis that takes the longest to reach its target position. So we have here axis number 2 in this example here. It's axis 2, axis 3 is green, and axis 6 is blue. So when moving from point 1 to point 2, the robot accelerates which hits the programmed max speed until it hits the programmed max speed, and maintain it. The lead axis will always the has the steepest acceleration curve to get the target faster, while other axes adjust to lower speeds to stay synchronized. So let's analyze this motion here. To start at point P1, axis 2, 3, and 6 begin their acceleration curves. Let's take a closer look starting point 1, axis 2 here. Axis 3, axis 6 initiate the acceleration phase. Once they reach that constant speed, they will hold it steady to stay there at a specific programmed speed. The lead axis stay at the max speed of the motion as it nears at the target point. And this acceleration speed, and the robot starts slowing down until it stops. Okay, so to recap, this is what happens when executing robot movement. Here's the cool part. If you watch it in manual mode, you'll notice that some axes move faster than others. This applies to all industrial robots. Right, moving on. Next, we have the approach zones. Okay, we mentioned earlier that these zones relate to the con parameter, the continuous parameter you set when creating a motion. Okay, we'll explore this in more detail in the KUKA simulator on later classes, but for now, remember, this is a universal concept for all 6-axis robots and also in KUKA, Fanuc, Motoman. Let's visualize this. Here I have 3 points, point 1, point 2, and point 3. When the robot moves from point 1 to point 2, each point defines the path and adjusts the approach zone. So imagine this setup here. P1 here, P2 here, and P3 here. That's our path here, okay? That's the path we're going to do. We'll cover the zones in depth later, but for now, let's give you the basics. So what you're going to do when moving from point 1 to point 2, then from point 2 to point 3. When you program these 3 movements and the robot execute them, if you're using the concept of approach zones, basically you're redefining a zone that tells the robot how sharply it should adjust its path between points. It's going straight from point 1 to point 2 and stopping completely on point 2, or it will allow it to have a approach movement, an angle here, like this cut corner, and take it as a shortcut, like moving along, saving cycle time. That's how you optimize motion passing from point 1 near to P2. It starts toward point 3 without passing at P2 directly. See, we have an efficient in the movement. Now, when should you use approach zones? Use them when you need speed and there's no collision risk. If you need a robot to stop precisely at point 1, skip the zone, don't use it, okay? Approach zones shine in free paths primarily where the robot can safely deviate from a straight line without obstacles to go faster. Larger wide zones mean wider angles and shorter cycle times. Smaller zones tighten the path, so adjust the zone type to balance speed and precision for your application. Okay, reduce the zone value if you need a narrow angle. Here you need more approximation, and increase it as the robot takes a more direct, faster route with more freedom to scale out. Okay, so the advantage is that you save cycle time because the robot's acceleration curve with acceleration constant speed and acceleration from point 1 to point 2 accelerates in a constant speed, then deaccelerates totally to get to point 2 and go to point 3 to start phases, add up acceleration and deacceleration times that will consume more time. So in your cell cycle time overall, when you make the robot stop fully at point 1 before moving to point 3, let's think practically, say point 1 is an approach point. What's an approach point? Imagine a gripper picking apart. It moves from the approach point 1 to the pickup, then goes to point 2, and at point 2 it must precisely stop to grip a specific part there, so then we cannot have any shortcuts. There it both needs exact position to pick a piece. So once there, it checks the part's precision and it activates the grip to pick up or to drop something at that point. So always use find zones for that type of applications because you need it. This ensures that the robot stops exactly at the point that you need it to stop. No deviation. Okay, that's non-negotiable for applications like that. So to recap, all pickup drop-ups require find zones every single time you will use movements for those applications. So this is an example of the balance between the angle deviation and the speed of the robot. Now let's check this out. Here's a move of the concept to visualizing to make it clear the times taken to do anything. So this shows what I mentioned earlier. Pickup and drop-up points requiring precise stops requires more. And here we have a motion with using approach zones, okay, without the precision. Notice how the robot maintains speed between points and this graph of velocity over time, okay? So the 30-second total, 30-second total, and the set motion instruction with find zones. Let's compare the two scenarios here. First, movements without approach zones. The robot accelerates and decelerates by heat and try to keep constant speed, but it just does it for point 1 to point 2, then it stops completely, so it takes like 11 seconds here, and the robot accelerates again and then maintains speed through point 2 and point 3, and then it deaccelerates again near point 3, okay, so it gets in point 3, and it's the same path, the total path was completed in 30 seconds here, so it was stopping in every point until point 4. You see, using approach zones, find zones, sorry, for precisions like that. But if you see here this type of movement, this you can see that it's much faster. So let's recap: approach zones, 1 accelerations. So we do 1 acceleration at one point, and then the program would move to all selected points using those angles and keeping a constant speed. Okay, until it reaches P4. So it reaches P4 in about 22 seconds here. So you see the difference? So when you're using a find zone, you took 30 seconds here, but with zones, it around 22 to 23 seconds. Same task, same paths, but here we have tolerance to perform some angles in our movements. In manufacturing, time equals money. So optimizing cycle time directly boosts up your bottom line. When we talk about streamlining a production line, it's all about trimming seconds out of your every motion, every interlock. It's add up. So one key task in cell optimization is auditing where to apply approach zones where we can widen our zones without sacrificing safety, okay? Where you can, when you need precision or when you need speed, Okay, so into multiply that overall shift, you see that if you do have a lot of application, even a 5 second reduction in one type of application, maybe you have this type of application in all your programs. So this could increase higher profits. So cycle time isn't just a metric; it's your lifeline. That's why zones and motion planning are critical for any industrial process. Now let's switch for a real demo. I'll show you how this works up on the KUKA robot. So let's see it in action. Let's divide it into the practical setup where we'll talk about zones, stat speeds, and how to optimize the path. Follow along. This is where the theory meets the reality. So let's see the results there. Let's see it in action. Okay. Alright everyone, back to the robot. This is our ABB simulator, as I mentioned. These concepts apply robot globally, so to all 6-axis industrial robots. So to master this in any robot, and you have mastered in every robot. So I'll use a routine here called Path 10. It's a pickup and deposit here. Notice that max speed and zone 200 settings, with zones enabled, the robot anticipate when the next move and when executing a current movement. So watch how it flows. Approaches the pickup point, grabs the part, and seamlessly transitions to the drop point. Now the pickup point here, this exact point, is critical. Max speed plus large zone means that the robot doesn't fully stop. But here's a quick, since this is a simulation, the part won't fall when gripped, so I won't overmind, so don't panic. We'll switch to zone find later on, okay? For now, let's run the simulation in auto mode and watch closely what happens with this form here, okay? So notice that smooth arcs, no full stops, but just continuous motion. Now let's compare to find zone behavior. Switching the parameters here with find zone, the robot stops precisely at that. So see the difference for speed and precision. So that's the power of motion planning. All right, starting the robot. Let's hit play. So what just happened? Notice how the gripper signal triggers even if the bot isn't fully stopped. In this simulation, the parts stay attached, so the virtual doesn't know if you can simulate the physics of where it starts grabbing, so it grabs where it was set to grab. Okay, so that's why it has this bug here. So let's reunite to highlight how zones work. Watch closely. With approach zones, the robot doesn't wait to finish one movement before starting the next. Smooth transitions, no full stops, but approach zones left the robot to overload acceleration and deceleration between points. It's always thinking ahead. While moving to point 2, it is already calculating the path to point 3. That's how you save off seconds. But in real applications, you need sensor for interlocks for safety, for example. In this demo, the logic triggers the DIO of the gripper signal based purely on position, no feedback checks. In production, your pairs like this with vision for non-sensor, so focus on motion efficiency and speed zone settings are your tools. Master this and you're 80% there. But remember, simulation is different than realities. Always validate your parameters on the real robot. Understand the second conditions, and not only to have nailed the programming and to need to optimize the parameter for each task, speed, zones, or everything. Let's break it down to make this clear here. I will slow the speed to 25%. Okay. Then around the robot, watch the position of the gripper. It's already ahead of the robot. Okay, notice how the pointer jumps forward in code while the robot is still executing earlier movement. See the manipulator icon here? The robot is at this position, but the pointer was already 5 lines below. That's the magic of zones. The robot pre-reads the next movements while executing the current one movement. So here, it moving from point A, but pointer's already planning to point B. Okay? It's like the robot's brain works a step ahead always, so pre-processing obviously increases the speed. Key takeaway here, zones lets the robot chain movement seamlessly, but to wake this alive, I'll switch back to manual mode. First adjust max speed, but wait, in some cases you can't just rank it to 100% by safety and precision first. So let's do it back. Let's see the adjustments. Switching to manual to set up speeds. Here's the thing, max speeds isn't always the answer. Balance is the answer. For the pickup, let's set a lower speed 10% here and switch to zone to fine for precision. The robot must stop exactly here before it poses the DO to grab the object. Okay, wait 1 second and then proceed. Okay, so I'll switch this to fine to pick up the piece, but in the next movement I can use Vmax or fine if I need, for example, to change the condition. So I'll put on V10% and zone fine. Okay, this next is also a precise movement, same settings for the head one, 10% speed and a fine zone. Adjusting parameters done. Now let's run the program again and see how it behaves. Let's put this also on V10 and fine. Confirm these sessions. Let's actually use Z10 here. So watch this. Fine zones, the robot moves always slower and waits to finish a movement before performing processing the other, before the pointer advances. Okay, so let's confirm the automatic mode and let's run. So now it is moving slowly on zone fine, so zones needs precision, but you're very slower in this application by using this V10 and fine precisely, but the robot will then move exactly to that piece, as you can see, and once it reaches there, it will pause the DO and execute the next movement after the wait instruction. So we have a precision exclusively on reaching that point that the program will pause the DO. Now it is moving using fine also to this next point, and notice that the pointer is locked in into this line until the robot stops the movement. Okay, then you go to the next one. So that's it, everyone. Notice I didn't touch the program's core structure or instructions. I only changed some parameters. Parameters are just as critical as the code. Beyond programming, you need to nail speeds, zones, and other settings for efficient robot operation, not just creating movements randomly. So this demo shows what happens when parameters aren't optimized for application. Okay. Always validate them in real, remember, real world tests. And quick note here, I arbitrarily set low speeds and zones here for clarity, not production ready values. So I show it in slowly moving here, but turning this into a very meticulous. But I can always juggle the robot in using these approach zones, but with higher speeds. Okay, so I can also adjust the speeds as currently. So I can add comments, for example. Comment, for example, approach point or ponto aproximação, português. So pick up point, the next one, So always, so anyone reading the code knows what those movements are doing actually. So this is always nice to have our software documentally for your team. Okay. Key takeaway: um, clear labels plus organized parameters is equal to efficient and collision-free workflows. Any question, drop down below. So let's optimize this routine. This program I wrote different. So I have approach point, ponto de aproximação. I have pickup point, ponto de pega. This is the pickup point. Got it? So clear labels, easier to debug or to improve this code later on. For documentation matters also. It saves us hours during maintenance having comments like this. So let's talk about fundamentals. Speeds and zones aren't just settings, they're core to collision-free operation. Here's why. In manual mode, a single line of code might turn flawlessly, but in production, unoptimized parameters cause chaos. So manual is different than automatics, which brings us to golden rule of robotics. Never skip parameter program. Burn this into your brain. Everyone working with robots needs these mindsets. Now, common questions. What happens if I program a motion in manual mode and run it as a single line of code? Okay, it will work perfectly, works great. You test it, everything seems fine. But switch to automatic mode and boom, then run unpredictably. Crop up movements, a lot of collisions or errors due to zones. So this is why you must always validate your speed settings and zones carefully. Common question. Can I set max speed everywhere and only use fine zones for pickups? And wouldn't that be faster? Technically, yes, but here's the reality. Without gradual acceleration and tailored zones, you get wear damage, okay? Because remember, those acceleration curves and accelerations, they create massive wear on the robot. So rapid accelerations on short bursts between points, um, for quick moves from one spot to another, that's okay, might seem efficient, but for those abrupt acceleration and deceleration cyclically stress the joints over time, and this leads to mechanical wear or even failures in your robot over time. Best practice: use higher speed for non-critical motions like a free space travel. Example, retracting the mill cutter here, raise axis 5 for example, or axis 3 to reposition, crank position, but for realigning and forming, slow it down for precision where needed. And bottom line, reserve max speed for safe open paths. Never use it as a default in your programming code. Instead, assign custom speeds to each motion, but base. So don't use it on purpose. Okay.